Hi everyone. Can you hear me? Can anyone just unmute and respond whether they can hear me or not?
Yes, sir.
Okay, yeah.
Yes, we can.
There are a few more people joining, it seems. We'll just start in 1 or 2 minutes. So, hi everyone. I'm Lalit, and we'll be discussing a few things related to week 1 lectures of the course Computer Vision and Image Processing, the NPTEL course. I hope everyone is here for the same course. Um, so yeah, as far as I've been told, this is an interactive session and not simply a tutorial. So of course, we'll do a few problems related to the previous week lectures, I mean week 1 lectures, but I expect that if you people to interact, ask a few other questions, or maybe if I ask a question, you people can respond to that. So since the course name is Computer Vision and Image Processing, what do you think computer vision means?
Hi, I'm Hisham here.
Yeah,
So let's start. I will try to give an answer. So computer vision is generally means if you use computer or some libraries to identify the images, we can call computer vision. Which
identify.
technique identify the images or image processing? It's called computer vision.
Not exactly. Anyways, anything else?
Enabling computer to see.
Okay, see, like humans, right? So that
Yes.
that's the main aim of computer vision. Like, and we want to replicate human vision, but of course we can't do it. I mean, we haven't done it yet. I won't say we can't do it. So based on that concept, that how human vision works, well, not how human vision works, but given an input to the human vision, how does it uh, interpret it? So that's the computer vision part. And what what about image processing?
So if we do any modification in image, it's called image vision. Sorry, image
I-
processing.
Image processing, yeah.
So processing means modifying the image in a sense to remove the blurring of the image, increase the intensity, contrast, brightness, and working on all those parameters and related to that.
Yes, there are different operations which come under image processing.
Yep.
So currently, since we are starting the course, so we are just talking about broad ideas. So image processing, yes, anyone else has anything else to say? Okay, so it's you can think of image processing as, yes, manipulating on the image plane to make more sense of that data. For instance, as someone said, you might want to change the contrast of the image, or you might want to denoise the image so you can see it more clearly, things like that. So image processing mostly deals with manipulation on images, and computer vision is mostly related to what that image says. So there are two different aspects to it. Like one, I think it was discussed in the class. One of them is like what is there in the scene. For instance, you want to segment and categorize something, like there is a table in the scene, or there is a cat given the given image. So that's one part, and the other part is depth perception. So given an image, whether you want to know whether this specific object is nearby, some specific object is far away. Of course, for computers, they are just a bunch of numbers out there, as they say that a 2D array, an image is a 2D array, but to interpret that, you need the vision part. Okay, so this is just a one-liner introduction of um, what image processing and computer vision means. So, okay, a few more people joining. Just a minute. Okay, okay, yeah. So the whole aim of this course is, I mean, of course, there are two aspects to it, the image processing part and the computer vision part. For computer vision, the aim is to model the problems mathematically so that we can then try solving it using a computer. And for for image processing, it's mostly related to improving the information content in the image, as I said, using different methods. Okay, so since we are on images, so what is an image?
Think
It's a 2D
digital
array.
digital representation
Yeah.
of light.
Okay,
So if
and
it is a gray image, so it's a 0 or 1, or if it is means if it is in color image, so we will add some additional attribute.
mm-hmm. Anyone else?
An image is a 2D projection of a 3D scene.
Okay, that's a better answer. Yes. Any other definitions? Yes, people can just
It's a
like
2D
unmute
array
Yes,
of
themselves and
pixel
speak
really.
out.
representation.
Sorry.
2D array of pixel representation.
Yeah. Okay.
Image
Any
is
any
the
yes. Yeah. Any other answer?
representation of light in form of 2D array.
Yes. Okay. So in general, image is a signal. Uh, we'll leave about the array part for now. So image is capturing what? Light, which is a signal. So like any other sensor, we have camera as a sensor for capturing images. Now it depends on which range you're working for. General range in which humans can see, that is from 400 nanometers to 700 nanometers. We use the simple RGB kind of a sensor. So that sensor actually senses what kind of signal? Analog or digital? What is light? What kind of signal does it give?
Analog.
Analog
Analog.
Analog.
signal.
Yes.
Analog.
So the initial part is that, yeah, we have to recognize that our input signal is actually an analog. Once we have that analog signal with it, then we would like to store it in a computer. I mean, previously in the old cameras, if you remember those film kind of cameras, they used to directly try saving the analog signal. Of course, I will not say purely analog, but in this digital era, we would like to digitize everything. So given that analog signal, what are the steps you need to do to digitize it?
S-
Quantization.
Sampling and quantization.
So which one comes first, sampling or quantization?
Sampling.
So okay,
Sampling.
what does sampling mean?
Sampling.
We'll
Yeah,
have a particular samples of that signal at a particular duration. We will
no.
break the
Here we are
signal
not
into
considered about
samples.
not considering time, given just signal which is varying with space. And there is no time variation out there. Okay. So yeah, you were saying something. Um, so what is sampling?
We'll take the means we'll break the signals into the parts and then we'll take that signals
Yeah, along what? Breaking along what?
along time.
No, here there's no time aspect as such since we are capturing an image. So I assume that the scene is
Along
static.
the
Breaking
intensity
into
of light.
segment.
No, no, no. That
Breaking
is
into
not
segment.
break segments. What are you breaking?
The 2D space,
Yes,
X and
yes,
Y axis.
yes. Actually, yeah. So when you are trying to capture the image, you have the light coming on a 2D surface, which is a sensor, right? But that sensor, you need to now, as someone said, break it down or discretize it. So that specific discretization is called as sampling. So you're just capturing specific rays in that 2D area, you can say. You're not sampling, you're not sampling infinitely so that you can capture everything. So the sampling part here is we are just trying to capture some of the rays that fall on the whole sensor layer. And what is the next step to digitize? So we have done sampling. The next is
Quantize.
okay. What does quantize mean?
Arranging those samples according to the
Sort of
upper and
discretizing the
lower bound.
intensity value, putting all the intensity values in a given number of buckets. Let's say we have 8 bits or something to store the intensity values. Then we will have certain number of buckets where we could put the all the intensity values.
Okay, but why do we need to do that?
Yeah, because we cannot deal with continuous data.
To
We
store the
cannot
image
process. We
digitally.
want to digitize the data, right? To process it.
Okay, yes. So computer memory store only binaries, which can be interpreted as other uh, bases as well. For instance, our decimal place, the base 10. So if you want to deal with it, you have to uh, quantize the signal value as well. So quantization is done over signal value and sampling is done over the space. So I hope this part is very clear. So when sampling is done and then quantization is done, well, sampling of space is done and then quantization of the signal is done, then we get a digital signal. So it has nothing specific to do with space. It can also be done across time. Like if someone among you have done digital signal processing, you generally see data which varies with time. So there you sample across time, and then the amplitude values are then quantized to get a digital signal. Similarly, here our signal is varying with space, assuming that our scene is static. So what do we get? We get a 2D signal, but this two dimensions is the space dimension, x and y dimension. And once we get this, we can yes, sample over the space and then quantize over the intensity values, intensity of light actually, and then what we get is a digital image. Okay, so since we are dealing with digital images, it's good to know that we know a bit about how it's formed. Okay. Um, so the next part is okay, how are the digital images represented? I guess this has been answered previously for the previous question.
Yes, sir. F of xy, this is the representation of digital image.
Yes, that's an abstraction actually.
As a
I
two
would call it abstraction. Yes,
as a 2D array. They are stored as a 2D array.
yes, as a 2D array. Okay, so what kind of images you have seen till now? What are the types of images that you've seen till now in the lectures?
Color, black and white, color,
Like
grayscale.
Gray level images, gray images, colored images.
Black and yeah. So yeah, the first is you binary images where you have discretization of just either 0 or 1 for the intensity value. The next is the grayscale image, where what are the intensity values generally used?
0 to
0 to
255.
255.
So which is equivalent to
0
what?
to 255.
Equivalent to?
Grayscale.
No,
255
grayscale is
equals
fine.
to white and 0 equals to black.
No, no. In terms of computer science, what would it mean?
8 bits
8,
8
information.
bit.
8
Raised
bits.
8
to
bit. Okay.
8.
So 0 to 255 means you can have 256 values. So for 256 values, you need 8 bits. 2 to the power 8. Okay. So and what's next? RGB. How many bits you need?
24.
24. Yeah, because you have 3 channels and 8 bits per channel. So how many colors can you represent using RGB image?
3. 3.
Infinite.
No, not
3.
3. How many total
Sorry,
copies?
sorry.
2 raised to 256.
It's
Sorry?
2 raised to 24.
Yeah, yeah, exactly
2
24.
raised to 24.
Yeah. So yeah, those many different color values you see, and for human perception, it's mostly okay, you can say. I will not say it's the best, but yeah, that's what people have been using it. Okay. So given this, so if I give you a 2D image, can you tell me 2D image of a scene? For instance, there are trees and there is a house. Is it easy to identify for humans whether which one is near and which one is far away?
Yes.
No, sir,
Yes.
Okay.
because the
Uh,
depth value is not given.
Larger the object, near to us.
are you sure?
No, sir, not always because sir, sometimes we don't know the like size of the image. Like if we have seen that thing previously, then we can like judge that thing. But if we haven't seen that thing previously, we cannot judge that whether it's like larger than what it should or whether it's smaller than what it should be. And if it's like random images, random squares and rectangles, then we cannot tell which one is nearer and which one is further.
Mm-hmm. Okay. Anything else? Anyone else
There
would like?
has to have some reference by which we can say that this is closer and this is far away.
Okay. Okay.
And
Okay.
depth
Yeah.
perception is also possible because we have stereo vision. We have two eyes. We take we take multiple images, and that maybe helps us.
Okay. Okay. That's actually right. I mean, you need other information. So just to motivate this, whether, I mean, whether we can really get, uh, what do you say, a feeling of depth just by seeing an image or not, I'll send this link to you, which you people can watch later, I guess, not during the tutorial. So this link shows that how things can be placed differently and still you can perceive things the way they want. I mean, the way the photographer wants and not the way you want to see it. Okay. So the problem here is that we are reducing the dimension. We are reducing the dimension, right? When we are trying to capture a 3D scene from a 2D image. So we are reducing the dimension. So we cannot clearly say that, okay, something is near or something is far. So if it's hard for us, I mean, if you can just check the video, you can say that it's not super easy for us to tell that. So how hard is it for computer? Because it's just a bunch of numbers, right? Uh, so that's what computer vision deals with. So given a single image, it's mathematically impossible to get what's the depth of a specific object in the image. But then given multiple images, you can do some mathematics to make sure that yes, we can recover the image out there. Okay, so I think these are some of the general introduction that I wanted to give. There are, of course, many things one can say about, but I thought that I should just motivate what we are actually trying to do in this course. Okay. Mm, so I think we can start with the problems that we have for today. Okay. Yeah, in case you people have any doubts, you can just unmute yourselves and ask me. And I hope you people are able to see my screen.
Yes, sir.
Okay. And is it readable?
Yes, sir.
The text is
Can you
readable?
increase the font size?
Yeah, font size is fine, right?
Increase
Okay.
it a little bit.
Could you please increase it
Sir,
a
please
little bit?
increase it.
It's not very
I
clear.
think this should be
Yeah,
fine.
this is fine. Yeah, thanks.
Yes,
Oh,
sir. Fine.
okay, yeah. So we'll just copy the image. Okay. So so you might have read about different distances out there in the course. So
Yes,
what
sir.
is Euclidean distance? What is the Euclidean distance? Okay, so we are for the current question, the context is given as like this. So we have an image, and for each image you have an index like this. So you have ith row. So the variable I varies along the row, and the variable j varies along the column. So, or maybe I'll use the notation used in the class. It might make it feel better. So the variable x changes across the row and the variable y changes across the column. Okay, people are still joining, I guess. Okay, yeah. So what is the Euclidean distance given any 2 points out there? So if I
So
call
now,
the first point x1 comma y1 and call the second point as x2 comma y2, what is the Euclidean distance?
root of x2 minus x1 squared plus y2 minus y1 squared.
Yeah, x2 minus x1 squared plus y2 minus y1 squared. So have you seen this distance anywhere else in any other subject?
Hero's formula. Hero's
Sorry?
distance formula.
No,
It is Hero's distance
coordinate
formula.
geometry.
Okay,
Coordinate geometry, we haven't done coordinate
coordinate
geometry.
geometry. Okay, fine. Any simplified version of that subject? Linear algebra. I think that will
It
be
is
the
Distance of
Hero's
for
2 point.
distance
Point.
formula in 7th standard we have seen.
Distance between 2 point in
yes, yes, yes,
coordinate system.
yes, yes. So how does this look like? It's like what? Taking what kind of norm?
Straight line.
Huh? Sorry. It's taking the L2 norm, right? Are you people aware of L2 norm?
No, sir. What's like we don't know about that.
No.
Okay, so yes. Okay, so how do so any norm, rather norm is a function which can be defined as uh,
So first of all, what is norm?
norm is a function. Norm is a function which helps us to define distances using different metrics. So I'll try to visualize that. Hopefully that can help you understanding this. So if you have done linear algebra, then I think you might know. Otherwise, I'll just state the definition. So if you have ith coordinate between two of these vectors, so there is a vector x and there is a vector x prime. So given these two vectors, if you can take that ith coordinate and then power it, so we call it as p norm. If you call it as p norm, just take the power p and do 1 by p of this whole expression. So maybe I'll just rewrite it here. It is the p norm of x minus x prime. So x minus x prime is the input. You can replace this with any other input and you can use this formula by replacing the specific p out there. So for the case of L2 norm, or rather we call it as LP norm. For the case of L2, how does it look? We'll square each of these differences and then sum it and then take a square root, right? And if you see Euclidean distance, it is of it looks similar, right?
Yes, sir.
Yeah.
Yes.
Okay. So if you replace p with
Yes,
2,
sir.
it looks similar like this. Okay. So this is something which is generally taught in linear algebra. So some of you might know it. So given this, okay, the formula looks quite simple. We'll just try to link this with others as well. What is city block distance? What is city block distance?
Sir, mod of I minus K plus mod of J minus L.
Yeah, so we'll
L1
just,
distance.
yeah, it is actually L1 distance. So it is, I mean, given this notation, I'll use x2 minus x1 mod plus mod of y2 minus y1. Is it right?
Yes, sir.
Yeah, okay. So
Yes.
which p norm relates to this? Someone actually said the answer.
L1 now.
Yeah,
L1.
L1 now. Yes. So that's how they call it as L1 distance. This people call it as L2 distance sometimes. Yeah, so this is also called as Manhattan distance. So there are many names to this, but the point is, given this framework of LP norm, we'll say it as L1 distance. Okay, so the third one is chessboard. Okay, chessboard doesn't really fit into this definition, but what is chessboard distance?
Sir, max of total I mod of I minus k, comma mod of j minus l.
So given this specific notations that we are using, is this right?
Yes, sir.
Okay, so we are checking for each coordinate what is the difference. I mean, absolute difference. We're taking mod, right? So we are checking the absolute difference and then we are taking maximum of it. Okay, so how do you visualize it? Euclidean distance. Okay, we'll visualize it one by one. I think that would be better. Okay, hopefully I can draw straight line straight. I don't know. Yeah, so I'll use different colors for different distances. So given point A and point B, uh, what would be the Euclidean distance? If you understand this formula geometrically, what does this mean? You people are able to see my pointer, right?
Diagonal distance.
Yeah, yes, diagonal, fine. You people are able to see my pointer, right? Okay,
Yes, sir.
okay. So since someone said diagonal, so I'll change it slightly. Fine. Given these 2 points, what is the Euclidean distance? How do you measure it? Distance like this.
Distance between
Just
point.
join
Yeah,
those
just
with a
the
straight
straight
line.
line joining these two, whatever is the length of the straight line. So this is what? L2 or Euclidean. Is this clear? Given the definition, this definition.
Yes, sir.
Okay. So next is city block distance. What? How should it look?
So first go horizontally, then vertically, or first vertically, then horizontally. That should be the.
Okay. Yes.
Y component plus X component.
Yeah. So you're just measuring the length of this lines, whatever I'm drawing. So you first go either horizontally and then vertically, or do the vice versa, but reach the same point. So the length of this green line, of course, the two line segments that they are the city block distance. And the next, what's the last one? Chessboard.
Sir, shift parallelly,
Maximum
like
of X
shift
or
that
maximum
parallelly
of
to
Y.
the shift one point parallel to the other one, and like there will be two cases. So the like maximum of the both cases will be the answer.
Mm-hmm. So how do you put it here?
In this vertical line is
Vertical line. Yes, that's true. And this it would be the vertical line. I mean something of this. So this would be the chessboard distance. And if you remember from the slides, so this would actually be radially equal. Yes. If you remember, if here the distance is 1, the next set of pixels will have distance 2, right? The next set of pixels will have distance 3. So it will be radially equal given this center point. Yes? I think it's done.
Yes, sir.
Yeah. And for Euclidean distance, it's mostly uh, up and down, left and right will be same, and the diagonals will have different values. For city block, it's how will it be? Again, the same like up and down, left and right will be same. The diagonals will be different, but the values with Euclidean and city block will be different. So okay, I think it's now clear how what geometrically means these three different distances. So now we can just plug in the values. So and find the Euclidean distance between two extreme diagonal squares of a given patch. So you can just take this as maybe I'll read off. So since we are asked about diagonals, right? So we'll just consider this and this pixel out there. So if I keep this as 0, comma 0, what should this be? 2, comma 0, and this will be 0, comma 2, right? So Euclidean distance is what? 2 minus 0 square,
2 minus
2 root 2.
0 minus 2 square, which is, yeah, 2 root 2. Fine.
2,
What is
2 root
city
2.
block between these 2 points?
4.
4. Yes, because you have to take this and you have to take this. Okay. Next is chessboard.
2.
2.
Yeah, because max is still the same. So it's the max of absolute differences in each coordinate, which gives us 2. Okay, so is this question clear? Any doubts to anyone?
Yes, sir.
No.
Yes. Yes, sir.
Okay, that's great. Uh, Next, what do we have? Okay, so this is something that if you remember, then you can solve it easily. I mean, there's nothing to solve. It's more about how do you remember it. Okay, the grayscale values of an image are uh, dependent on what? The first option is proportional to the total irradiance and unaffected by foreshortening factor, inversely related to distance between the object and the lens, inversely proportional to the distance between the lens and the image plane, or it is proportional to the scene radiance and foreshortening factor. Okay, it's too hard to read like this. So I'll ask you first this. What is foreshortening? Well, there is a factor that's been used, cos theta, I know that, but if you can tell me what does it physically mean, I think it will be better to remember it.
When we see at an surface, it looks smaller when it is tilted towards us.
Like it,
Yeah.
like it's the projection when we project like the base on the baseline when we project that thing.
Baseline. Okay.
When a
What do you mean
surface
by that?
is inclined towards us, it looks smaller. That is called
Yes.
foreshortening effect.
Okay.
When we tilt the source or the object, then its area reduces. That effect is known as for shortening factor.
Mm-hmm. Mm-hmm. Okay. That's right that if you tilt uh, the if you have a surface which is hollow, for instance, you are just taking a small rectangular piece and then trying to move it or rather tilt it in a specific direction, you might not see the area projected. The area projected on your eye is 0. So I can put it in a different way since we don't have such nice illustrations out there. I'll just try to use a good old blackboard style illustration. So assume that this is a unit sphere or any sphere out there. Okay. Um, so given this specific line, okay, yeah, given this specific line, I place an object here. It's infinitesimally small object. You can think very small object. So what is the projected angle out here? What I mean by projected angle is something like this. Okay. This, I mean, if you just try to project the two extremes and the line and the angle segment obtained from this segment is theta. So this is some theta naught initially, right? This is some theta naught that you actually observe. But now if you try to move this object vertically, and probably it reaches somewhere here, how does what would be the projected angle? Hmm? Did it reduce? Yes.
Yes, sir.
Okay.
Yes, sir.
Yeah. So did it reduce, right? So if it goes to infinity, then how will it look? A projected angle?
Point 0. Angle should be 0.
Here,
Yeah. The angle will be
It
zero.
will tend to 0. Yeah.
Yeah, it will tend to zero. Yeah. Okay. So this is the idea of foreshortening in the sense that based on how you are seeing it, your object is tilted, right? So you can think of this as your eye is here. So with respect to your eye, this object is being tilted. So given this tilt, you can see that the effective area that you are able to see reduces. Or rather here the effective angle reduces, and when you go in 3D space, the effective area reduces. So that is the foreshortening effect that's being specified. Okay, so coming back to the question, so gray values of an image are what? So can you relate? Where was this? In which lecture was it specified?
second lecture.
Lecture 3.
Yeah, lecture 3. It's on radiometry actually. Okay. So if I, so what is this E? What was this denoting in the lectures? It is im image irradiance, right? Whatever is the irradiance captured by the image. It is the irradiance captured by the image.
Illumination.
Sorry, did anyone say anything? Okay. Fine. So this is the,
Lightning part of surface.
sorry, lightning.
Lightning part of surface.
Um, yes. But here in this specific case, this, yeah, that's true. So this is the part where, I mean, it denotes how much bright the surface would look like. So
Yes, sir.
if your surface is way too bright, then of course the image captured will also be bright. Yes, you're right. So given this, uh, so we have what? Proportional. What is this D?
Diameter of
Yeah.
lens.
No. Are you sure?
Yes, sir.
Okay, yeah, it's the diameter.
Yeah, it's diameter of the lens.
Okay, it's the diameter of the lens. What is FP? FP is the distance between
Distance between object and image plane.
um,
Lens and image plane.
lens and image plane. Yeah. Okay, I should write image plane. And what is alpha? Alpha is the foreshortening angle.
Foreshortening
Yeah, angle.
angle.
And so the cos alpha is foreshortening factor that's been specified. And what is L?
L is radians.
Yeah, L is the radiance of the scene. Okay, fine. L is radiance scene. So given now you know all these different parameters, now I think it's easy to realize what are the options, correct options. It's inversely proportional to the distance between the lens and image. Yes.
Yes. Yes.
And
The first one, proportional to total irradiance and
unaffected?
unaffected by foreshortening.
Well, it's affected, right? We have a foreshortening factor here.
No.
This is the foreshortening factor, right? Cos
Yeah,
alpha.
yeah.
So what should it be? The fourth one.
Proportional, yeah.
It's proportional to the scene radiance and foreshortening factor. Okay. So yeah,
Mm-hmm.
this is valid in what case? What was this? How was this formula derived? What are the assumptions? Hmm? So this is valid only for thin lens, right?
Mm.
It was mentioned in the class. So yeah, when you model your irradiance like this, so it and given a lens, you have to make sure that your lens is thin enough. Otherwise, this formula may not be valid in real life. Is it fine?
Yes, sir.
Okay. Okay. So next question. Okay. So you are given a 42-inch square TV. I guess many of you have such big TVs. The video frame is of size 6000 cross 6000 pixels. What does video frame means?
6,000
One,
rows and columns of data.
yeah.
Yeah, so each individual image
Yes.
in that video is of this size,
Yes.
6000 cross. That's what it means. So given that, and you're given a 42-inch big TV. So what is the resolution in PPI? So I should define PPI before I can ask this question. It is pixels per inch. So this is very important. So if a seller tells you that he has 100-inch TV, he's giving you at a pretty cheap cost, then you might want to think about how good the resolution is. So this resolution matters a lot for the viewing quality. Okay, so what is the PPI for this given question? How do you calculate? So what does 42 inch mean? What what does it even mean? So
Diagonal.
my
The
TV is
aspect
a
ratio diagonally.
yeah,
Aspect ratio.
yeah, it's not really the aspect ratio, but yeah, it goes diagonally. So it's the
It
distance.
goes diagonally.
Yeah, it goes diagonally. Yes. Have these tools. Let me just make use of this. So this distance is what is given to you as 42 inch. Given this 42 inch distance, now you have to see Now, how do you get pixels per inch? What is this? This is 6,000 pixels, and of course, for our case, it's a square TV, and this is also 6,000. So, how do you measure pixels per inch now?
Multiplication of both and divided by total area.
Okay. Uh, Anything else? I want just one number, not two numbers. So if the screen is, what do you say, rectangular, then you might have two numbers, right?
Applying Pythagoras theorem or no?
Okay. On what?
Simple, we can take any sine or a cos theta. We know the diagonal. We can find the other two lengths, and then we can multiply, and
Mm-hmm.
we'll get the area.
Yeah, yeah. Sine theta cos theta is simple here because it's a square. What would it be? It's 45 degrees, right? These are 45 degrees. And this is 90. Hopefully the TV is not defect piece. It's a 90-degree square. Given this, so yeah, instead of taking cos or sine, I'll do it the other way around. So what would be the hypotenuse in terms of pixels? It would be
Yes,
6,000
6,000 square.
squared into 2,
Yes.
right? So it's 6,000 root 2. Do you agree?
Yes.
So this is in pixels, but we
Mm.
have the same quantity in inch.
Yeah.
Yes, so both should be same. So what's PPI then?
Divide by 42.
Yes, 6,000 root 2 by 42. Yeah, we need a calculator, but it's fine. So is the idea clear? How do we measure pixels, or rather the
Yes.
resolution on TV? Okay, great. Move on to the next one then.
It's all the question I have posted in the chat.
Oh, sorry, I'm not checking chats. Let me check it once. After this question, I'll look to the chat. Okay. Okay. Someone asked, can you explain again? Okay, what part do you want me to explain again? Okay, fine. I think I'm not getting a response. So yeah, we'll do this. Okay, PPI. Okay, great. So what do you want actually? So you want that how many pixels you have per inch on this TV screen. So given that, you can find how good the resolution of the TV is. So we have two different quantities out here. One is a 42-inch square TV. That means the diagonal of the TV is of length 42, and the other information that we have is this size of the TV. That means the length and the width of the TV. Given the length and the width is given in pixels. So since it's a right angle triangle here, we can just compute the hypotenuse, which is, maybe I should write the full thing out here. Might clarify things. So it's just this base square plus the height square, which gives us the hypotenuse, which turns out to be 6,000 root 2 pixels. But this 6,000 root 2 pixels should be same as that of this diagonal, which is 42-inch. So both quantities should be same. So what do we need? We need pixels per inch. So how many pixels? So per inch you have. So we have to divide the number of pixels by the number of inches that you have for the TV, which leads us to this quantity. I hope this clarifies the question. think we can move on to the next one. So the brightness of a Lambert-Eaton surface is indicated by what? BRDF, which is constant, and 1 by pi times of the reflectance coefficient. BRDF, which changes
Correct.
according to the outgoing radiance. BRDF, which varies inversely to the change in reflectance coefficient, none of the above. What is BRDF? Hmm? A full form of BRDF at least?
Bidirectional reflection
Reflectance
distribution.
distribution function. So if we can break each of the component, what does it mean? Bidirectional. That means you need both the directions, input and the output directions. So the function, whatever function it is, they use this Greek letter rho, but whatever way you want to define. So it depends on input direction. Maybe they first write the output theta I, theta 0, phi 0, or theta O, phi O. O is for output, and theta I, phi I. I is for input, right? So this is bidirectional. This makes it bidirectional. Reflectance, of course, how much light is reflected. That's, I mean, that's what this quantity is trying to specify. Distribution function. Distribution, why? Because for every value of input and output directions, you can get the reflectance out there. So it gives you an overall distribution of how the reflectance varies with these quantities. I hope the name is quite clear now. Hopefully, yes, because I tried to break it down. Okay. So yeah, just once more, reiterating that bidirectional means you need both the input and output directions, reflectance, because you're trying to get how the lights are being reflected, and this quantity models that. Distribution function, because for every value of input and output direction, you can find the reflectance out there. So that's why bidirectional reflectance distribution function. Okay, so enough of trying to break it down. We'll move on to what the question is. So what does Lambertian mean?
The surface
This is
which doesn't reflect in a single direction,
Uh, Sorry, the surface?
which doesn't reflect the light in a single direction. For example, cotton.
yeah. It
Uh,
is independent of the angle actually.
what angle?
Reflects,
There are four
independent
angles.
of the direction.
Which direction?
The light gets reflected in all like the path of the rays is independent of the
Well,
direction.
input or output?
Output.
What about input?
Uh, it applies to input as well.
Yes.
It's
So,
like irrespective,
sorry?
irrespective of like the
Yes, yes.
input.
It's completely irrespective of the input and output directions. So, given a light source and given an object which is a Lambertian, which is Lambertian object, you can, independent of where the light is or independent of where you are trying to view the object, it will give you the same BRDF. So BRDF is constant for Lambertian surface. That is the definition of Lambertian surface. So okay,
Can you
so
give example other than the cotton?
okay, other than cotton, so if you see your walls, how does it look? Just look at a patch of your wall. I mean, I hope that your walls are not painted with plastic paint. If it's just normal paint out there, you can see on the walls, irrespective of the direction in which you move your head, or irrespective of the direction in which your
That
light is there,
wooden,
it won't
wooden is the best
matter.
example of that.
Sorry?
Wooden material without paint.
Wooden materials without paint, yes, that's also true. But if you, yeah, without any polish on it, it also looks similar. Yes, that's right. Or blackboard, if you have seen blackboards, the blackboards, the old blackboards, they don't reflect that much. They are, you look, I mean, you can see the same thing in whatever direction you have or whatever lighting condition it is. So I'm not talking about the brightness level. Talking about the variability given with direction. Of course, now the brightness will depend on how much light there is in the room and other factors. So, okay, so I think this is completely fine that BRDF is constant for our case, and you remember the derivation that's done in the lecture, it turns out to be uh, rho. So rho d is, this is the rho by pi, where this rho is the BRDF of Lambert-Eaton surface. Okay, any doubts on this question? So yeah, someone posted a question. We'll do a similar question and after one or two intermediate questions. So yeah, don't worry. We'll do it before the class ends. Okay. Okay. We'll go to the next one, I guess. Okay. What is radiant flux? Before we move on to this question. Yeah.
Amount of light
Mm.
exhibited by the light source.
Uh, mm, okay. Not really. It has nothing specific to do with light source. Of course, light source will have a radiant flux, which is fine. What is radiant flux? What is the unit of radiance flux?
What?
Watt. So, anyways, yeah, you can see it from the question.
What?
So,
Yeah.
what does it mean?
Energy per unit
Energy.
What
per
is the
unit
unit?
area.
Flux is basically incident of light on area on particular area.
Okay. Okay. What is the unit for which quantity?
Power.
Power. How do you say that? What is defined as joules per second? Joules is the unit of
Energy.
energy. Yes. So energy per unit time is power.
Power.
It's an easy way to remember this. At least for me, it's easy way to remember this. Yeah. So yeah. So what does radiant flux means? physically it's a power. It's the amount of power that specific light contains. Yeah, now of course the point here is that we generally get power from light sources, so you can say the amount of power that light source gives us. But yeah, that's fine. I think that's a simple definition. So moving on, we have a radiance flux of 100 watts. So the usual notation used for flux is 1000, I mean phi 100 watts. What is the irradiance of an object which is placed 2 meters from the light? What is irradiance then?
d5 by dh
Amount of
means
amount of
area saved by
radiant
the
flux
radiation.
in radius.
There's some noise. Yeah, someone was saying, can you repeat?
Amount of
सर
flux
100 वाट को
incident on
एरिया
the
से
area.
डिवाइड करेंगे उससे।
Okay. The one person is having some issue with microphone, it seems. I'm just not able to hear that. Anyone else?
Can I say?
Yeah.
Radiant flux per unit area.
Okay. Yeah. Someone else also wanted to say.
Yeah, radiant flux per unit area, but on the object means not from the not on the light source.
Yeah. So area means you need to have an area out there. So there should be a surface. So it's on, you're measuring it on the
Uh,
object.
this is three-dimensional area, solid a solid angle. If we consider the projection of the that object on the sphere,
Yeah. Unit
Yes.
sphere.
Area of the sphere.
that is
Yeah. So the effective area of the sphere, that's what is out there. So it's defined, irradiance is defined in what unit?
steradian.
Huh?
Sorry, sorry.
So watt by meter
What
square.
Watt by
what
meter
is
square.
Yeah.
what
Watt by
steradian?
meter. Yes, that's right. Okay. So we'll move ahead first, given that we have a radiance flux. What is it that we need to do? Hmm, we'll first calculate radiant intensity. So are you given any surface area out there of the object? I
We
don't
have
think
to
so.
calculate because it's
No, we are not given any information about the surface, right? We are just given this information that it's placed 2 meters
two
away from the
meters.
light.
Yes.
So we
Yes.
don't have any information about the surface. So what can we do? So that's why I
We'll
will
consider
start.
it as a sphere.
Yes, yes.
We'll consider it as a sphere.
Okay, you might want to complicate things, it's fine, but ultimately I'll take the easy way. Probably I'm lazy, so it's okay. So radiant
So
intensity is what? Phi by omega, right? Well,
Hmm.
d phi by d omega.
D5 ID.
I mean, how much flux changes per unit steradian. And or how do you define steradian? There. What is the, how do you define solid angle?
For a
Area
sphere, it
area
is
by r
4
square.
pi.
Mm-hmm.
Area by r square.
Yeah. So if you take very small area dA and then you divide it by r square, so you get the solid angle. And how does it come? What's the usual definition of angle? This is the definition for steradian. What is the usual definition of angle in radians? This is three-dimensional equivalent of angle. Angle is angle exists in 2 dimensions.
Small arc divided by radius.
Yeah, it's the arc length
Arc
by
length. Yeah. Hmm.
arc length. Maybe I don't know what notation to use. I'm just writing arc length upon the radius r. So this quantity is defined in radians, and this is defined in steradian. So it's just the three-dimensional equivalent of the usual angles that we have been seeing since childhood. Okay, so what's the total solid angle that you can have? I think that was derived in the class. You integrate over a sphere, what will you get? What's the total angle in 2D? What's the maximum angle?
0 to 360,
360, or in radians?
2 pi.
2
Yeah,
pi.
0 to 2 pi. So in solid angle, how do you get it?
It's 4 pi.
Yeah, it's 4 pi. So if you integrate this over the whole sphere, then you get this as 4 pi. You can just try it out. It's already given in the lectures, so I can just take that as well. So what we have is the radiant intensity as 100 by 4 pi, and units is watt per steradian, right? Is this fine?
Yes.
So from radiant intensity, how can we get irradiance? What is irradiance?
Pi divided by this solid angle, omega.
Mhm.
Radiant intensity by r square. That's
How did you arrive at that? Irradiance is what?
d.
What's the usual definition of irradiance?
d psi by dA.
Yeah, d phi by d, or I'll just remove d here because we are taking the whole surface out here. We are taking the aggregate and not specific small values. The irradiance is phi by a. Okay, and then this radiant intensity is phi by omega, and omega is what?
5 by omega.
Omega is, it's here, solid angle,
2 pi.
a by r square. Yes,
1 pi.
I mean, I'm not
Yes.
taking small angle, it's a
Mm.
big angle, so I'm just writing a by r square. Is it fine?
Yeah.
So with this, I think someone said that relation. Can you get the relation? What does it mean? So phi by omega is what? Radiant intensity, which is phi by a into r square. And phi by a is what? Is radiance into r square. So you get a new formula out there. Irradiance is radiant intensity by r square. Okay. And what is this r, by the way? R is the
Like radius or
radius,
the
or
distance.
yeah, distance
Distance. Yeah.
between what? Distance between the light source and the object.
Distance between the light source and object.
Yes. So it's the distance between the light source and the object. And this area, what area A you see, is the area measured on the object. For the specific question, we are not given that. So that's why we are going this long route. So radiant intensity we have already calculated 100 by 4 pi. And what is R for the question? 2 meters. So again, divide by 2 square. It turns out to be nearly, I think, okay, how much? 1.99. Yeah. So is this fine? Is this question fine? Any doubts? Okay. So we move on to the next question, which has similar things. So we again have radiant flux, which and I have an object which is placed 2 meters away. So what does this mean? The irradiance is same, right? We have just used these two quantities out there to compute irradiance. It has nothing to do with the object size. Irradiance is still the same. It is, well, I can write it as one. And then we are given the size of the object as well. Okay, now we have a 20 cross 30 centimeter rectangular object. So what do we do? Light source has, what is the flux? Okay, we need to find flux now. What do we do? Irradiance is phi by a, right? So the flux phi is, okay, what is the unit of irradiance? Watt per meter square, we discussed it just a few minutes back, right?
Yes, sir.
Yeah, so we have watt per meter square out here, and then irradiance into the area of a rectangle. So we just have to multiply the area out there. But we are given in terms of centimeters, so we'll convert it into meters. Area of a rectangle is width into height, right? Okay, so yeah, so whatever this quantity is, what would be the unit of flux? What is the
That
unit of flux? Watt, yes,
mm,
it's watt. It's a power. It's power. Flux is power. How much power you have in that light? Well, rather here in this case, how much power is been received by the rectangular object? Okay, fine. Any doubts in this question? Okay, then we'll move on to the next one. Okay, so given a 10-watt source means again, since you now know clearly that 10 watt means you're talking about flux out here. So we'll use the flux phi, which is given as 10 watts, coming from a solid angle. So the omega is 2 pi by 3, and steradians, of course, of radius 3 meters, corresponding. Okay, source of this coming in a radius 3 meters. The corresponding source of energy is carried by the. What does this ask? So you're given a 10-watt source with the subtending a solid angle on the surface as 2 pi by 3, and the radius here means the distance between the source and the object. The source of energy carried by the ray is what? So what is the source of energy carried by the ray? It is the radians. So we need to compute radians out there. How will we compute radians? What is the formula for radians? L is something what? Hmm?
d square phi divided by dA into cos theta.
Okay,
dA and d omega into cos theta.
someone read this out, d square phi upon dA cos theta and
Sorry, dW omega.
d omega. Okay.
Yeah.
What does this even mean? D square phi upon dA cos theta d omega.
It is irradiance into
No. I mean, not that way. What does it mean mathematically? Having d square phi out there, and then you have dA out there in the denominator, d omega in the denominator. What does it mean? What is the unit of radians?
watt per steradian.
And area. Area is also there, right?
Per meter square.
Yeah.
Yeah. So watt per meter square into steradian. I mean, meter and square and steradian are in the denominators. Okay. So that means what does it say? So how much power varies with respect to the solid angle subtended and also with respect to the area, also per unit area of the object. Does this make sense? How much power of light is being carried per unit area of the object per unit steradian? That's what radians means. Okay, so given that, we'll first find the area since we have what solid angle. So we have solid angle as 2 pi by 3, which is what? Well, what is cos theta here? We are assuming that there is no foreshortening effect, so cos theta should be 1. Given this, a by what? R square? Yes, we are given radius r as 3. So what is the area? 2 pi by 3 into 3 square, which is 6 pi. Fine. This is what the area of the object on which the light is falling. And once this is known, what do we need to know? Now we can compute radians. So radians L, maybe I should just write radians L is what? Now can you tell me, just seeing the units, how do you compute radians? It is phi by per unit area and per unit steradian. Yes? Phi is 10, area is 6 pi, steradian is what? 2 pi by 3. So we'll have it 3 by 2 pi. Turns out to be 5 by 2 pi square. Is it right? Um, any doubt in this specific question that how we compute radians? So
Sir,
how
it
much?
will 5
Yeah.
by 4 pi square.
Sorry.
Sir, the answer of the radians will be 5 by 4 pi square after
Why 5
calculating.
by 4? I mean, we have this 3 out there. 2 turns out to be 5. 5 by 2 pi.
Okay, sir.
This is fine.
Sir,
Just yes.
sir, how did you calculate the area?
Area is given since we know the uh, steradian out there, the solid angle subtended. So the solid angle is given as the area subtended upon the distance between uh, distance between the object and the source. So given this thing that we know, we have this radius 3 meter, which is not the radius here implies the distance between the object and the source. So we can compute with this formula. Is this fine?
Yes, sir. Okay. Thank you.
So we have given any, okay, 3 meters, yeah. So area is 6 pi meters square, not written the units. And radians is what? Watt per meter square into steradian. Okay, we'll move on to the next one. Uh, okay, so this one should be pretty simple given that we did a previous question similar to this. And after this, we'll do the question which was posted on the group chat. So we have a light source which has radiant intensity of 60 watts per steradian. Determine the irradiance of a signboard 2 meters away. What it should be. We derived some simple formula there, right? This one. Can we use this one? We have radiant intensity. We have the distance to the object. So can we get the irradiance? I think it's irradiance is what? Radiant intensity upon r square. Okay. So yeah, radiant intensity is 60 watts per steradian, and this turns out to be 2 square, which is in meters. So yeah, our this turns out to be 50 by meters, watts per meter square steradian. Is this fine? Yeah, someone asked, will the recording be provided? Yes, it will be provided. It should be posted uh, on the course announcements page. recording, and also this note, whatever you are seeing that I'm writing, it will be provided there. Okay. Next is the question that was asked.
Excuse me, it's
Yes.
irradiance is only watt per meter square, right?
I do something wrong.
It's not per steradian. The unit of irradiance.
Okay, sorry. Yeah, yes, sorry.
Yeah, thanks.
Watt per meter square. What? Uh, intensity should be in watts then. I think here some problem.
Yeah.
Sorry about that.
Yeah, that's true.
Yeah, sorry. Okay, so we'll move on to the next. Okay, the next question is, suppose we have a source with an area 4 meter square. Again, another mistake. It should be meter square, it can't be meter inverse. Is viewed at an angle of 30 degrees and has a radiance of 0.3 watt per meter square, the radian inverse. Calculate the radiant intensity of the source. I think this was the question that was asked here. Okay.
Yes.
So what do we have? So viewed at an angle of 30 degree, that means you have the theta as 30 degree. So you have that foreshortening effect. And yes, given this, we have source area as 4 meter square. Source area and radiance, which is denoted by L as watt square steradian. Okay, intensity is so what is the formula for radiance?
L equals to d square phi by dA cos theta d omega.
But we don't have the information of omega.
Then we can use the one you have calculated in other example, something.
Omega is A by R square. We can calculate.
What is R?
Oh.
So okay. Radiance should okay. intensity.
First, we'll calculate the flux,
Mm.
and then from that we can calculate.
Can you calculate flux?
Yes.
How can you calculate flux? Well, the effective area, at least we can find it out first, which is what? Effective area is A cos theta because of the foreshortening effect. So A into cos 30. Cos 30 how much? So 3 by 2. 2 root 3. Okay. 2 root 3 meters square. Given this effective area, now what? Radiant intensity. Okay. What is the unit of radiant intensity? Flux is watt and watt per steradian, right? So what do we have here? This is flux per unit area. Well, effective area. I'll write it effective area because the area is, you have to consider the foreshortening effect into steradian, the solid angle. That's what we have written it earlier, right? See, radiance is flux per unit area and the effective and the solid angle out there. So here we need to use the effective area. And what we need to get is radiant intensity, which is what by definition it is flux per unit steradian, right? Yes. Yeah, that's how it is defined in the class, d phi by d omega.
Yes.
So I think now it's pretty simple. Okay, so it's 0.3 watts per meter square steradian into 2 root 3. This is watts per steradian. Is this clear? Yes?
No, sir.
No? Okay. So do you agree with the formula for radiance? So whatever we discussed here, see, this is some quantity which is varying with area and solid angle, right? So when you take differentiation, you write d phi by dA and then d phi by d omega. So it turns out to be d2 phi by dA into d omega. So this whole thing is the effective area. It's not effective area because we have foreshortening effect here. So assuming this is not there, so your actual formula is what? Phi by A into omega. Yes?
Yes, sir.
Yes.
Yes. So don't just get carried away by the fact that there is d square of phi. This just denotes that this is varying with A. I mean the effective area, and this is varying with the solid angle as well. That's what it signifies. Doesn't mean that you are squaring the power. Okay. So given this, we yeah. So given this, we have this specific formula that given a radiance, overall radiance phi and overall area A with the solid angle subtended omega. So you have this formula phi by A into omega. So given this phi by A into omega, and for our specific case, since we have it is viewed at an angle of 30 degree, we have the foreshortening effect. So we have to use the effective area. The effective area is then calculated as A cos theta, which turns out to be this, yeah, which turns out to be this quantity, and then you can just plug it in the uh, radiance formula to get the radiant intensity, phi by omega. I hope this is fine.
Yes, sir.
Okay. Yeah, someone posted the same question again. It's the same question that we are solving now. So I think it should be fine. Okay, let me see. Do you have any other doubts apart from radiometry? Since we are just doing radiometry in the question. So I think this course probably assumes that you know basics of image processing, low pass filters, high pass filters, uh, Fourier transforms. I have not checked the full course, but as far as I know, the basics of image processing is not covered fully. So do you know what low pass filter means? I mean, anyone can speak out.
It attenuates only
Filters
low
frequency.
values. Filter which attenuates only low pixel.
Low values of what?
It attenuates higher values
Signal.
and passes low
Low
values.
values of signal.
Low values of signal? No, that's wrong. Someone else who was saying something?
Frequency filter.
See, low pass filter passes the low values of any, if you can
Low values of?
consider amplitude, if it is a,
No,
sorry,
no, sorry, that's not correct.
if we consider a frequency, low frequencies it will pass, and higher frequencies it will cut off.
Yeah, yes. So when we say filters, low pass filter, high pass filter, specifically in the context of image processing or signal processing, we mean the low frequency content or high frequency content. Low pass means you're passing the low frequencies and blocking the high frequency part. And the vice versa is for the high pass. That high pass means that filter passes the high frequency part and then what do you say? Mm, blocks the low frequency part. So just to give you one intuition, because since we are doing image processing, you might want to know what low pass or the low frequencies and high frequencies look in the images. So we'll start with the 1D signal and we'll move on to the 2D signal. If I have a signal like this, my signal is pretty distorted, but you can think of it like enough of drawing it to do this. So this is some signal which has this periodic. This is the periodicity, right? Let the periodicity, let the time period be t. So what is the frequency? How do you define frequency of this specific periodic
1
signal?
by time
1
period.
upon T. 1.
Yeah. So what is, I mean, how do you measure time period? Seconds, right? So this is time and this is amplitude. So time period is in seconds. Frequency is 1 by time, which is measured in what?
Hertz.
Hertz.
Yeah. Thanks to the famous scientist Hertz, we kept this name on as honor. Okay, so what do you see here? How many? I mean, you can see that this is some signal which has time period t, but can you try breaking up this signal? Is it even possible to break up this signal?
Yes, we can sample this signal.
No, no, no. Don't. I'm not talking about sampling. Just assume that this is, we are just working in the analog domain. So this is some signal out there, and you want to break it into its components. Components in the sense that can you add two signals to get this signal?
Yes.
Yes.
Yes, because I said so. Because I
One,
asked this question. Yes, but
one
why?
is positive side signal, one is
No,
negative
no.
side signal.
Okay, that's fine. But anything more? Since this is a periodic signal, can I add two periodic signals to get this periodic signal?
Yes.
What are those two periodic signals? Can you just, I mean, give a rough idea so
Plus,
that I can draw
we
it?
can yeah, we can have sine and cos. And
No, I just want simple answers. I don't want mathematical expressions. How would the first signal look like? Yeah, it's sine and cos mixed somehow in this case, but
yeah, okay. First will be the sine wave and second a triangular wave.
yes. Yeah, so first is this smooth sine wave which varies pretty slowly. Well, the second one also varies in a similar manner, but the point is it is not that smooth. You have peaks and then it goes like this, and then this is this. So the second one is not a sine wave. You have some other factors, but both are periodic signals. I hope people agree on that, right? If we add these two signals, you can get this signal. Agree?
Yes.
Yeah, I mean, my diagram might not be accurate, but at least you got the idea. So, given this, what do you think? What are the frequencies of the two signals?
Frequencies are same.
Yes, frequencies are same. It's just the amplitude. Frequencies are same. Amplitude is different. So I think with the next example, it will be pretty clear about what I mean about amplitude and frequency and filters and all. So next, now I want to generate something else since I want to keep the frequency different because I want to show you an example. That's the only reason. So given this, I'll just have the same axis, y-axis, so that it becomes easier to uh, show up. So I have this specific signal, which varies like this. Probably I'll have another signal which has a higher amplitude than this. So let this amplitude be A. So this amplitude be 2A, maximum amplitude. So how would the addition look like? See, at zero, it
Uh,
will be zero, right?
At any given point in time, we are just adding the two amplitudes.
Multiplying, yeah.
Multi
Okay, sorry.
adding.
Um, okay, yeah. My example is for addition. Okay, yeah, fine. We can add it. So, how will it look like? So the peak will somewhere be here, right? After this and before this.
Yes. Mhm.
There will be no negative
No
component in the signal,
negative, no
or
negative signal.
Why? This is going to 2A, right? Minus 2A. Still go negative component because this amplitude is only 1A,
okay.
right? So I don't know whether I can draw this properly. Just try
Will be kind of notch filter or
no, whatever it is. So my main idea to show is that you can express any signal into some of its constituent signals. So these constituent signals will have some basic frequencies out there. So here the frequency is, uh, if the frequency is f here, the frequency for this signal will be 2f, right? Yeah, because the time period is opposite. Okay. So yeah, so if you can have, I mean, any signal can be represented as the sum of its constituent signals, which is what is given by the Fourier series. For Fourier series, it's given, it says specifically for periodic signals. And in general, you can have Fourier transforms that even for non-periodic signals, you can break it down into its constituent, what do you say, signals. So now I'll just give you another intuitive example that this is one signal and this is another signal varying with time. So which signal do you think has high frequency component and which signal will have does have low frequency component?
Left side would be high frequency one.
Yeah, but why do you say so?
And because it is more irregular.
Yes, yes. So what is frequency? If you can just define frequency apart from what we saw earlier, one by time period.
it's
Frequency
one upon time.
at a,
One upon time.
That's okay, but yeah,
how, how many times a signal repeats itself in a given time interval.
yeah, yeah. So in a given time interval, how frequently things change?
Yes.
Sir, I have a question.
Yes.
These frequency definitions change for signal. Let's say we have an image and
Hmm.
we have audio signals.
Okay.
These definitions are not so concrete in the like what is frequency in image.
So it's the same actually. It's just that independent axis changes. So for audio signals, it's generally varying with time, right? So the time is you check
Mm,
frequency with respect to time, but for images or any other
But
thing which varies with space, you check frequency with respect to space. How the signal varies with respect to space.
now what will be the definitions with respect to space and
It's the same. It's like it's one by the, what do you say?
one by
Previously it
one
was
by
time period, but now you can say in general you can say instead of time period, the period in which the signal repeats. That's it. There is
time
absolute.
period. What is sir? What is time period in image and
So here
uh,
remove time and then you can say space period probably. No one actually defines it that way, but
yes.
when the signal starts repeating
And
after a particular,
one
yes.
one more thing is that uh, here we are showing that we are breaking up signals into different frequencies and
Hmm.
weighted sum will be generate signals that we want
Yes.
and there are also papers aside that we add up some neural networks and we also get signals now. Sine and cosines are converted into threshold functions and it's also not clear what are why only sine and cosines are used for the weights weighted.
Okay. Okay. So I think that is kind of digressing from what we are doing here. If you ask me about neural networks, there are many things people have done, or rather,
What
humans
is
engineering being
actually
done.
a constituent actually is it a sine function or is it a neural
It is
network? What
it
actually it
is
is?
not necessarily sine or cosine. It can
What?
be any function out there. So there are different class of functions. Now, if I start using some weighted sum of sines and cosines, you can say it as Fourier's. You Fourier defined it like that. But then there are other kind of functions like wavelets. So wavelets are different functions. They are not sine and cosine, but they still add up to give you the same function. So there are
Only
different
thing is
yes,
that
yes.
we are mixing things to make a signal. But no matter what is the constituent we are making.
So it's like if you ask me in linear algebra that given a vector space, so how many different bases you can have? There are infinite number of bases you can have for a given vector space, right? So now I can see, now I can take for 2D case, if x and y axis can be my basis, or if I can tilt x and y axis by 45 degree, it still remains my basis. So in a
Yes.
similar way, if you can, I mean, signals can be represented in multiple forms. The point is the class of signals will now be that you can represent with specific functions will be limited by the basis functions, or rather the constituent signals that I'm talking about. That's why there are two different transforms: Fourier transforms, cosine transforms, and then wavelet transform. And then there is Z transform as the Z power discrete. Well, that's a completely different thing. My aim here is just to give you an intuition. If
Okay,
you
thank
really want to do that, you should do a signal processing course, basic signal processing.
okay, okay.
Okay, yeah. So as someone was saying, yeah, this will contain high frequency component. Uh, this will have high frequency component, and this will have low frequency component. Why? Because things are not varying so much in the right signal, but things are varying so much in the left signal. So now I give you two images. I'm just extending this. Now, what is this t? T, you can say it as time, or you can say one of the axis, x-axis, for instance. And but now, if I give you an image like this image is completely black. And the next image that I have is strided black. So this is black, the rest part is white. This is black, and the other part is white. So which one do you think high frequency component? So this is X and this is Y for the image. The amplitude is determined by the color.
Left, right side has some periodicity, but left side do not have.
So left side doesn't have any variability, so it is just single low frequency component present out there. For right side, if you now go across this specific line, you see that the intensity values changes. So there is frequency in the X component of the signal out there. Yeah. So you can actually visualize signal when you see visualize how frequency works for images. If there is too much variation in the images, then you can say that there are high frequency component out there. But if the image looks pretty similar, then you can say that the frequency component is low. For instance, if you just take an image of a sky, it will be it will mostly contain low frequency component if there are no clouds. But if you take a image of a street, then there are so many elements out there, so it will create high frequency component. Okay, I think that's all I have for today. We'll join next week at the same time with the next set of questions and probably some more intuitions on the upcoming lectures. Any doubts for today's lecture? Yeah, okay then. Thank you very much for joining. These recordings and the specific notes, whatever I'm making here, will be made available through the course announcement. Okay, thank you very much. Good night.
Thank you. Bye.